ATS EVS students, this is Dr. John Schrage, and I love paleoclimate. It's just a great subtopic within the study of climate and climatology and so on. This is all about the climate of the past, and it's just a really cool topic. I have actually taught a course before that was about abrupt climate change, and when I was in graduate school I took a bunch of classes in paleoclimate because I just thought this is a really cool topic. And as it happens, we have a recent graduate of Creighton University's Atmospheric and Environmental Science programs who now has her PhD herself working in the field of paleoclimate. It's just a really cool subdiscipline. Now, I hope you enjoyed the readings that were on pages 26 to 31 in your textbook. If you haven't had a chance yet, please do so. Feel free also to look in the IPCC assessment report. Chapter 4, I believe it is all about paleoclimate, advances in paleoclimate in recent years, and it's actually really quite interesting. I recommend it. I don't require it, but I certainly recommend at least getting a sense of the kinds of information that are there. This paleoclimate stuff is really interesting, this climate of the past stuff, because you got to wonder, how can we know? I mean, how could we know what the climate was like during the Ice Age? How can we know? I mean, I guess we could tell by like geologic evidence that there were glaciers, but how do we know what the temperature was, or how much snowfall they got per year, or what the carbon dioxide concentrations in the atmosphere were back then, and so on? What kind of observations do we have that can tell us about the climate at that time? What kind of inferences can we make from observations as well? All that kind of fits together into this module of the course. I'm going to tell you that there's going to be 4 kinds of observations that leave records of what the climate has been doing, and we're going to talk about each of these in some detail over the next few minutes. Let's start with the satellite record. By the satellite record, I mean literally as in like satellites in orbit around the planet and so on. The first satellites that were used for meteorological purposes were in the 1960s. Fairly shortly after we started launching satellites to catch up with the Russians, we launched weather satellites. The first ones mostly did things like take pictures of clouds from space, but they also have instruments on board that can take other kinds of measurements. We started doing that in the late 60s, but it really wasn't until about 1979 that there was a global effort to make these observations consistent and archive them so that they'd be available for the future and so on. And so those kinds of observations that come from satellite really don't have that long of a period of record. If we stick with our definition that climate has to do with having 30 years of observations, we've kind of only just recently passed that point with regard to satellite observations, where we can start talking about like a satellite climatology of precipitation, or a satellite climatology of ozone concentrations, or one of the other things that we do in fact measure using satellite remote sensing. It's not just images, there's all kinds of sensors on board that can be used to infer things like the winds and the temperatures and ozone concentrations and so on. So I mean, while the satellite coverage is wonderful and it's a modern tool, it only goes back, maybe 35 years that we actually have permanently stored satellite data. So that's not really a good tool when we're talking about paleoclimate. Now we have the instrumental record as well, where we're talking about actual calibrated in situ observations. Mostly we're talking here about thermometers, but also rain gauges or tidal gauges on at a harbor or something like that. These kind of high quality in situ observations just don't go back terribly far, at most a few centuries. It really wasn't until the mid-1800s that it was very much fashionable in science to be very systematically, in a very coordinated way, be taking observations of the natural world. It just wasn't really how science was thinking about problems before then. And so a lot of modern weather stations got established in about the 1840s, 1850s, or something like that. That was also a big era of exploration and so on, so that tends to be where like a lot of stations opened up in the tropical Pacific, or India, or Africa, or South America, or so on. We typically have these kinds of observations back at least a few centuries, 150, 180 years, and then, European centers of learning like London, or Paris, or Berlin, well, there they might go back, 300-400 years, or something like that, where they have routine observations of things like temperature and even pressure, or precipitation, or something like that. But that doesn't really help us understand global temperature anomaly going back, maybe 12,000 years on this particular plot. Now, the gray shading around there, that's some kind of error estimate, but Well, how in the world are we getting this? Or how, even more so, there's another figure that comes from your textbook. I mean, this extends back 400,000 years. We clearly don't have satellites and thermometers and rain gauges that far back. In heavens, there's a similar diagram I got from your textbook that extends it back 4 million years of temperature records for the world. And in fact, here's one that goes back in your textbook even back to 70 million years ago. Heavens, dinosaurs were walking the Earth 70 million years ago. How on earth are we getting these kinds of records? Well, clearly we're not getting these from, calibrated thermometers and rain gauges and stuff like that. Rather, we have to use some kind of proxy for that kind of information. Humans leave records that can be proxies for climate data, and the natural world leaves signs that can be used as proxies for the climate in the past. Now, this word proxy might be something that you're not really all that comfortable with. Just to pull a definition of proxy up, that first definition, the ability to represent someone else, that's not exactly what we're looking for here. Definition 2 there, a figure that can be used to represent the value of something else. Okay, we're going to be able to use something else we see in the natural world to relate it to the temperature that was going on, or the precipitation that was going on, or something like that. Now, when we're talking about humans and the kinds of records we leave behind, they typically are actually historical records. I mean, people are really good at documenting their world, and, for example, missionaries in South America left these Franciscan missionaries and so on in places like Peru and stuff like that. They kept meticulous records of exactly how much their harvests were each year and so on, all the way back to like the early 1500s. So, okay, we don't exactly know how much it rained in, Peru that year, but we do know that that was a very good year for their grapes harvest, or it was a very poor year. And in fact, we don't just know, it's great or it's poor. We have very precise numbers. Well, we can actually, infer from there things like where there were dry years and wet years and so on, or warm years and cool years, or whatever. The monks kept very good records of that kind of thing. Another example is the so-called Nilometer. Egyptians monitored the height of the Nile, and they kept records of this for more than 13 centuries. This doesn't go all the way back to like the people who built the pyramids. This is more like since the beginning of Islam. But the Egyptians, their livelihoods depend on the height of the Nile, or they did anyway at that time, because the prediction of the annual flood of the Nile had a great deal to do with like when they were able to plant crops and when they were able to harvest crops in the Nile Delta and so on. And as a consequence, very carefully monitoring this sort of shaft that was dug near the Nile that would then fill with water from the Nile, and they could measure how many steps up that shaft were covered with water from the Nile, helped them know how high the Nile was. Well, the main thing that determines how high the Nile is stuff, principally how much rain is falling upstream in like Ethiopia and so on. So we can use these records of how high the Nile was as a way of saying how much rain was falling in that part of the world. Okay, there's lots of these kinds of historical records. Digging these kinds of things up is a whole sub-discipline within climatology. But when you really want to go farther back than that, you need to be using what we call paleoproxies. Paleoproxies are these long-lived chemical or biological systems that have information about the climate imprinted onto them. And it's probably easiest to talk about paleoproxies if we just give some examples. For example, the ice that is in a glacier or an ice sheet provides useful climate information dating back to the time when the snow fell that became part of that ice sheet or whatever. See, scientists go out to these glaciers and these ice sheets with specialized drills that can pull out a big long plug of this ice out of the ice sheet. You can kind of see one up here. It sort of augers down in there and it pulls out, I don't know, they're about 15 feet long, these shafts, these cores of the ice, and they can then go deeper and then go deeper and pull these cores out. Now, it's quite a project for a scientist to figure out how to identify how old is the ice in each place here. There's a lot of techniques to doing that. They can look for things like volcanic ash in the ice, that they know that a volcano erupted at approximately this time, and then they see the ash in the ice. There's a lot of ways in which it can be done. But if you can determine the age of the ice in each layer, then you've really got something. This picture that's in here is from the National Ice Core Laboratory, which I believe is in Denver. I've never actually been to that particular facility, but you can see how they have in cold storage all these long cylinders of ice, these ice cores that they extracted. I have actually been to a similar facility in Columbus, Ohio, the Bird Polar Research Center. And no pun intended, it's really cool. I mean, there's a lot of really interesting ice cores that have been extracted from glaciers all over the world. And when you take a very close look at them, you can see that the ice has some structure to it. That's what that diagram up there at the top is. You know, there's often, for example, an annual cycle to fresh ice and snow being deposited on the top, and then in the warmer season, there's sort of some melting that makes a crust that freezes back on once the short warm season is over, and you kind of get these layers to the ice. Okay. Characteristics of the ice are going to be able to give us climate information. They could be things like its chemical composition. They can be things like little bubbles of air that are trapped in the ice, and so on. These kind of ice cores can provide us with climate information going back about 800,000 years. The oldest ice on Earth is about 800,000 years old. That's about how fast the big ice sheets of like Greenland and Antarctica go and then reach the sea. You know, they form and then the ice reaches the sea and calves off as an iceberg and floats out to sea and melts. So we don't have climate information from ice cores farther back than about 800,000 years, but as is talked about in Chapter 4 of the IPCC report, we can actually get a lot of really interesting information from these ice cores. Now, for example, I mentioned the bubbles. There's little pockets of air that are very carefully extracted from those ice cores. And that air, sometimes the expression used is fossil air, which is totally cool. I mean, it is air from the time that ice was deposited. And we can capture that air, extract it from the ice core, and then analyze it. How much carbon dioxide is in this layer? How much methane? How much other gases in the atmosphere? And what we can learn from that is that present-day concentrations of atmospheric greenhouse gases, like carbon dioxide, methane, and nitrous oxide, currently exceed the range of concentrations recorded at any time in the last 800,000 years. Wow, that's really interesting. So we know that at least in the last 800,000 years, we've never seen concentrations of greenhouse gases in the Earth's atmosphere like what we're seeing now. Perhaps more importantly, the current rates of increase in carbon dioxide, methane, and nitrous oxide are unprecedented. There have been times where the concentrations were going up, and there were times where the concentrations were going down, but the rate of change has never been what we've seen right now. Again, it's very hard to picture that somehow whether the climate change that we're seeing is natural, when in the 800,000 years that there are natural records, we never saw that before. Doesn't mean it's impossible. We're going to see that there are other strange things that have happened in the climate of the past, but this is certainly a clue that this is certainly an unusual thing going on our planet right now. There are other examples of ways in which we can extract paleoclimate information from the natural world. The natural world can serve as a paleoproxy. Another example is ocean sediments. You know, for example, where a big river dumps into the sea, sediments that were carried by the river then settle out down to the floor of the ocean, and they accumulate at the floor of the ocean at known rates and so on, and they contain all kinds of stuff. And scientists can drill cores in the floor of the ocean and bring up these sediment cores and analyze them. Things like there's microorganisms that are dead and are in those sediments. They have like skeletons that are composed of certain minerals. What species of microorganisms were living at that time? We can learn things about the chemistry of them. We'll learn about that in a little bit, but like the chemistry of exactly the materials that make up their shells and so on of these little microorganisms is another example of the kinds of paleoclimate information we can extract. And we can be learning a great deal about the whole area that river drains from the sediments that then fall down into the base of the ocean when that river meets the sea. Another example is corals. You guys know what corals are, right? Like a coral reef. These corals grow at very slow rates, and the composition of their little exoskeletons and so on depends on the temperatures of the water they're in and the carbon dioxide concentrations of the water and so on. What species are thriving at any given time? What species are weak? Well, coral gets fossilized. We can dig cores through the coral reef and find older corals farther down, and we can learn important things about like the water temperatures and you know, the acidity of the ocean and so on by understanding those corals. Now, when I talked about ice cores and little exoskeletons of those microorganisms and the corals and so on, a couple times there on the slide said that we can learn something from the chemistry of those materials. I want to give an example of that. Water molecules, H2O. There's a cartoon kind of right there drawing it for you. There's a water molecule right there. Got 2 hydrogen atoms and 1 oxygen atom in it, but all oxygen atoms are not the same. Turns out on Earth there are 2 main types of oxygen atoms. Type is a bad choice of word. Let's use the correct word, isotopes. There are 2 main isotopes of oxygen. If you're not comfortable again from like a high school science class with the word isotope, isotopes are one of 2 of more forms of an element that contain the same number of protons in their nucleus, but different numbers of neutrons. What determines what that material is, in this case oxygen, is how many protons it has. The number of neutrons can vary. And in the case of oxygen, there's 2 main varieties. There's oxygen-16, which has 8 protons and 8 neutrons, and there is oxygen-18 that is 8 protons and 10 neutrons. They're both water. They're both oxygen, and when you hook them up to 2 hydrogen atoms, they're both water, but they are not exactly the same. For example, oxygen-18 weighs more because it has 2 more neutrons in every nucleus. But on our planet, some of the water molecules, the oxygen atom is an O16, and some of them it's an O18. Now they occur on Earth in some known ratio. There is a certain number of O16s and O18s in the world, and like, you know, you take up ocean water from the ocean, there is a known ratio between these 2 materials. I'm drawing it here as if it's half and half. It's not half and half, but they'll give you the idea. So the 16s that I've got that are floating in the ocean are supposed to be water molecules with a oxygen 16 in them, and the 18s there are supposed to be water molecules that have an oxygen 18 in them. All right, it's all water. You can drink it. Well, I mean, this is ocean water. You can't drink it, but it's all water is water. It doesn't matter which isotope of oxygen it happens to have in it. But there's differences between this water. For example, when it is cold, these 2 different forms of water, having 2 different kinds of isotopes, 2 different isotopes of oxygen in them, evaporate at different rates. When the temperatures are low, relatively little of the water that contains oxygen-18 will evaporate. On the other hand, you know, more of the water that contains oxygen-16 will evaporate. So like up there in the atmosphere there, I made it so that most of the water vapor molecules floating around in the form of humidity and so on are oxygen-16, with just a little bit of it being oxygen-18. Okay? But if I make the thermometer up there on the left side of the screen go up, and so we're talking about a warmer situation, when it's warm, a lot more of the water containing oxygen-18 evaporates. So the temperature is what's going to be determining the ratio of oxygen-18 to oxygen-16, well, water molecules containing oxygen-18 and water molecules containing oxygen-16 in the atmosphere. If the world's oceans are warmer, there's relatively large amounts of oxygen-18. When the world's oceans are cooler, there's relatively less oxygen-18 in the atmosphere, just because these 2 different isotopes of oxygen, when they're bound to 2 hydrogens and make water, they evaporate at different rates. Well, every single water vapor molecule in the atmosphere eventually falls out in the form of precipitation. So that snow that fell on a glacier and became part of the glacier, that's water vapor that used to be in the ocean and then evaporated. So if the atmosphere was mostly water vapor that contained oxygen-16 and some water vapor that contained oxygen-18, the snow will be just like that. And so if we can go into our ice core here again, extract little bits of it and determine the ratio of water containing oxygen-16 to water containing oxygen-18, we now know what the world's ocean temperatures were at the time that that record was taken. That's amazing. We can actually figure out what the global ocean surface temperature was from ice that's been laying there under an ice sheet for potentially hundreds of thousands of years. This is really cool that this works. And in the same way, actually oxygen atoms are also incorporated, for example, into the exoskeletons of microorganisms. Okay, the materials that the little creature used to make his shell they uptake things like water molecules into the minerals and so on that they make their shells out of, and we could use the oxygen ratios, the different isotopes, to determine the temperatures of the water that creature was in. Certain other minerals work the same sort of way, like the minerals that are in coral and so on. That they'll have different ratios of different isotopes depending on things like what the temperature was. Another example of a paleoproxy for climate information are tree rings. The study of tree rings is a subdiscipline within climatology. It's called dendrochronology. Dendrochronology is actually, assembling a chronology, a history of the climate based on trees. And you probably know the basic story here. I mean, trees grow a certain amount each year, and as the trunk of the tree grows each year, it makes a ring. And so the width of these rings tell us something about how much the tree grew. Now, trees grow different amounts based on a number of factors. You have to know a great deal about the trees to be able to attribute the width of each of these rings to what was going on. For example, some trees are very keen on the temperature. How much they grow depends on the temperature of the area. A narrow ring means that the temperature was outside the range in which the trees grow. Maybe it was too hot, and a thicker ring means that it was more in the temperature range that the tree thrives. Maybe it's more about the precipitation. But all these trees can be studied, and then we can find trees, extract cores from the trees, or cut trees down or whatever, and we can then say, well, the outermost ring of the tree is the current year, so then we can work our way backward all the way back to when the tree was first, started growing. And some trees live thousands of years. I mean, we don't have such trees in Nebraska. We don't have such trees where I live in Indiana, but I don't live in the sequoia forest or in a redwood forest or something like that. Not only that, we can actually find old trees or old wood that has been cut down and find overlap. So, for example, like the paleoclimate of Ireland can be determined for at least a few hundred years farther back by taking living trees and then comparing their tree rings to the tree rings they see like in the rafters of very old churches. And they can find, okay, here's the same rings on those trees, where here's, maybe 7 bad years in a row followed by 2 really good years. Okay, they can find it, and then, okay, we now know these trees overlap. And from that we can extend the records even farther back if we need to. In some cases, what we find are fossils of trees, like petrified wood and so on. Now, fossilized tree rings can't be pinpointed to a particular year. I can't look at any given ring on this tree and say, oh, look, 7,323 years ago was a bad year. No, but I can tell if this tree is from approximate, maybe by radiocarbon dating or something, I can tell that this tree comes from 72,000 years ago, and I can see that there was all really big fat rings, and then I can say, look, the conditions were very favorable for that tree at that time. I can't pinpoint it to a particular year, but I can show you the kinds of conditions that existed when that tree was growing. And with paleoclimate records like this, man, we can do all kinds of cool things. Like we can build these kinds of reconstructions of the paleoclimate of the last, about 1,200 years, for example. And you can see that there's a number of different sources of information on this graph, like tree rings and glaciers and so on. And they aren't all in perfect match, but they have the same basic trends and so on. For example, all of them seem to show the medieval warm period. Now, the medieval warm period is a period that was, centered roughly around 1000 AD or something like that. And particularly in Europe, they had a fairly warm climate. Not quite as warm as the present climate, but compared to most of human history, a pretty darn warm climate, especially in Europe. It wasn't really quite as global as some climate anomalies, but it was definitely very favorable for medieval culture. I mean, people in medieval times lived a pretty primitive life, and fortunately the winters weren't that bad in Europe and so on at that time. In contrast, for example, there was a period called the Little Ice Age. Now, the Little Ice Age spanned from about 1500 to about 1820 or something like that. And the Little Ice Age was a much less favorable time, especially in Europe, but actually globally. Temperatures were considerably lower than modern times. At that time, for example, the River Thames through London froze every year. They would have winter festivals out on the Thames River because they could have it out on the ice, and there'd be ice skating and markets and stuff like that. Well, I mean, the Thames, I don't even know when the last time it froze. Certainly not in the last, like, 50 years or something like that. I mean, the climate is much too warm in Europe nowadays for that to freeze. The Little Ice Age was really bad news for, like, the Vikings. Okay, the Vikings really relied on being able to take their big clumsy ships up and down rivers to go and sack villages in France and so on. Well, if the rivers were freezing during the winter and so on, it just wasn't good for Vikings at that time. The Little Ice Age is not a true ice age as we're going to see, but it's a nice term, the Little Ice Age. When you actually take a look at these graphs here, you get a sense of just how crazy the current climate change really is. Compared to the last 1,000 years, we are really, really increasing temperature fast. And our temperatures are really quite high compared to the last 1,000 years. Actually, to put that even in further context, take a look at the last 12,000 years. Look at the climate change that's happening just in the last, few hundred years. I mean, the spike is practically straight up and down on that temperature diagram there of the last 12,000 years. You can see that in the few thousand years leading up to the modern era, the climate trend, globally, the temperatures were trending downward. It's over a period of 6,000 years or something like that. So, I mean, it was a very slow climate change, but it is true that the climate was overall trending downward in terms of the temperature. Whereas, like, earlier in human history, before the beginning of written records and so on, if you're getting to be like 8,000, 9,000 years ago, well, there was actually quite a nice climate optimum going on, where temperatures were quite warm. I mean, obviously there were winners and losers in terms of the climate then, just as now, but there was certainly a very long, prolonged time where there was reduced glaciation and so on. What I think is actually interesting about this, though, is where was this coming from? If you go a little farther back on this diagram here, you start seeing, wow, we're coming from some really cold time, right about 12,000 years ago. From about 12,900 to about 11,700 years ago, there was a really interesting cold period called the Younger Dryas. The Younger Dryas is a strange little climate anomaly that happened about that time, where especially Europe and North America went back to very cold conditions. The Ice Age was over, and yet for about, maybe as much as 1,000 years, it was suddenly very cold again in Europe and like the eastern United States in particular, although there were climate problems all over the world at that time. That particular climate change actually has been tracked down to a breakdown of the so-called Thermohaline Circulation. The world's oceans have an overall pattern to their currents that redistribute heat and salinity and so on all around the world. And in particular, the Gulf Stream, that current at the surface, that warm current that goes up the east coast of the United States, broke down for a few thousand years, or a few hundred years anyway. And that brings warm water from the Gulf of Mexico up the east coast of the United States and over towards, especially England and Scandinavia and so on. And that current just broke down for a couple hundred years. It's actually very, very fascinating as to why it happened and so on. Wow. Climate was terrible for a couple hundred years there, or maybe as much as 1,000, and people were around by then. They weren't keeping written records yet, but the Younger Dryas is actually a really interesting phenomenon. It's an example of a phenomenon that we call a stadial. A stadial is a term in climatology that means a cooler period. This isn't a true ice age. There weren't ice sheets 2 miles thick over the upper Midwest or anything like that, but it was a cooler period where, glaciers were advancing, where crops would have been failing, where certain species were experiencing extinctions, etc. A period of maybe on the order of a few hundred years where something like that was happening. In contrast, if you have an ice age going on and there's a little gap in it where maybe things are getting warmer for a couple hundred years, that's called an interstadial. So a stadial is the cooler period and the interstadial is the warmer period. And they're both on the order of about a couple hundred years. I mean, that's what we're talking about when we're talking about stadials and interstadials. In contrast, if we take these same kind of records and we extend it back, let's say, 4 million years, you start getting a sense of how crazy and complicated the paleoclimate system is. I mean, that last little dip that I have highlighted in red there, that whole thing is the so-called last glacial maximum. When you hear the term ice age, that little dip, that's it. That little dip there is about 100,000 years of ice sheets covering most of North America, Europe, Northern Asia, and so on. It started about 100,000 years ago, and it reached the last glacial maximum, which was about 25,000 years ago. By some definitions, by the way, we actually are in an ice age, because we are currently in a period where there is permanent ice on Greenland and Antarctica and so on. There certainly have been many periods in Earth's history where there's been no ice at all. I'm not trying to say we're in an ice age. I'm just saying by some definitions we would actually be in an ice age right now. But I mean, you can see we've had plenty of periods of time where it was cold. Don't get me wrong, the most recent ice age was actually a bit of a doozy as ice ages go. But scientists have actually documented literally hundreds of ice ages, each maybe on the order of a few 100,000 years long, over Earth's history. Wow, ice ages just keep happening. Just to use this term right here, an ice age is a prolonged stadial, typically on the order of a few tens of thousands of years to maybe a few 100,000 years long. And it's going to have things like very low temperatures, big thick ice sheets, and so on. And that's in contrast to the periods between ice ages, which are called interglacials. An interglacial is like the period, it's like a prolonged interstadial. Okay, an interstadial is only a few hundred years, an interglacial might be a few tens of thousands of years. There have been lots and lots of ice ages in, the history of the Earth. The ice ages, as I have on here, typically last about 100,000 years. The cooling going into an ice age typically tends to be fairly gradual. The ice sheets don't just sort of form over the course of, I don't know, I mean, you don't suddenly 100 years later have a 2-mile thick ice sheet over Minnesota. They take many, many centuries, many, many thousands of years to reach the peak of the ice age. Interglacials tend to happen fairly fast. The ice tends to retreat, the melting happens fairly fast, but the interglacial itself does tend to be shorter than the glacial period as well. Why does all this happen? Why do we have all these ice ages that have been going on for the last, certainly for millions of years, and actually we have every reason to think all the way throughout geologic history of the Earth? The primary reason has to do with changes in the Earth's orbit. Everybody here has been in a class where we've learned about, how the Earth rotates and revolves and it goes around this orbit and so on. But the exact parameters of the shape of the orbit and how far the Earth is from the Sun and the tilt of the Earth's axis actually changes quite a lot over geologic time like this. And there's some patterns to it, but it's also somewhat chaotic. We'll learn more about this when we talk about the physics of climate. But most ice ages are fairly well attributed to, that was when we can study back to the Earth's orbit and so on, we can see, oh yes, at that time we would have also been somewhat farther from the Sun, or we would have been tipped more towards the Sun in the summers, or so there would have been more melting. All these things can be tracked based on these cycles of the Earth's orbit. Part of the story, though, is also carbon dioxide. On this graph, the solid line is a record of temperature. I believe this comes from Antarctic ice sheets. And the trace of carbon dioxide is shown, concentration is shown there in the dotted line. And carbon dioxide, an important greenhouse gas, pretty much shows exactly the same thing as the ice age records. So carbon dioxide is certainly a big part of the story as to whether or not the planet is in a glacial or an interglacial period. But there's actually several really cool extreme events in Earth's history in terms of climate. I'm just going to talk to you real quick about two of them. One of them is the so-called Snowball Earth, where basically the whole Earth froze. There's some question as to whether it may have, did it really freeze all the way to the tropics, or did the tropics have, fairly bad winters, but still everything melted in the summer? Okay, we're talking something that happened 650 million years ago. There wasn't even all that much complex life in the oceans yet at that time. So this is a difficult period to study, although it's certainly an active period of research. But the Earth apparently froze in a very complicated climate feedback, and we are actually incredibly lucky that the Earth figured out a way to get out of that mess. We'll learn about these kinds of so-called albedo feedbacks when we do physics of climate. But Earth at least once froze like Hoth from The Empire Strikes Back. I mean, it was an ice planet, Earth, for quite some time. For at least a few million years, Earth was stuck in that kind of frozen state. Excuse me. Another really weird climate event is this little spike that happened about 56 million years ago in the temperature record. It's called the I always get the name wrong, Paleocene-Eocene thermal maximum, the PETM. Something happened on Earth about 56 million years ago. This would be about roughly 9 million years after the extinction of the dinosaurs. Climate in general was quite warm at that time on Earth, but all of a sudden there was a very sharp spike of a few degrees Celsius, and we can tell from various things about the sediments that collected at that time at the bottom of the ocean and so on, that there was a massive influx of greenhouse gases at that time. A massive increase in greenhouse gases and a temperature increase, a very short temperature, very rapid increase of a few degrees. There were mass extinctions, especially in the ocean. If this doesn't sound familiar, yeah, this sounds like us. This looks like what is happening now. A very rapid increase of greenhouse gases. We're doing it by fossil fuels. We're not quite sure what happened at the PTEM. It might have been volcanic. It might have been a collapse of a methane calthate deposit. We'll talk about that at a different point in the course as to what's going on with methane ices at the bottom of the ocean and so on. But something happened, and enormous amounts of greenhouse gases got released into the atmosphere, and the temperature spiked. In many ways, this is the one that has climate scientists worried, because this looks like what's happening to our world, and we know that a lot of creatures didn't make it through this climate event and so on. Overall, though, what does paleoclimate tell us? Paleoclimate overall is telling us that the last few decades of the 20th century were warmer than any comparable period during at least the last 400 years. Okay, we have really good instrumented observations, at least enough that we can say certainly we're warmer than we've been any time in the last 400 years, and maybe since the medieval warm period. We didn't have thermometers in the medieval warm period, but boy, it sounds like we're even warmer than that period. Earth certainly has been both much cooler and much warmer than what we're seeing today. That doesn't mean, though, that it's not, oh, well, then I guess we don't have to worry about it all that much. No, we need to worry about it. The critters that lived on the Earth at those times did not thrive when the world was, you know, climate was changing in those ways. But we know that where we are headed is in the range of things the Earth can do. Okay? Earth's climate clearly can get this warm and warmer. Earth's climate can get colder than this as well. The current warming is extraordinarily rapid compared to most of the events that have happened in the paleoclimate record. There are some interesting climate events, known interglacials and so on, that were similarly fast. Typically they were caused by something like a volcanic eruption or a comet impact or something like that, where, you know, things changed one day. And now the ice sheets are retreating because there's there's more greenhouse gases in the atmosphere or something like that because of the volcanic eruption or whatever. But compared to pretty much everything that's ever happened in Earth's climate, what's happening now is really, really fast. Like hundreds of times faster than the climate changes we've seen at other times that were clearly natural because we weren't here. That's really scary. Okay, I mean, we're trying to make sure we're trying to make sure if we know if the climate changes we observe are natural or if they are anthropogenic. That's another really good reason to suspect that the climate changes we're seeing are anthropogenic. Looking towards the future, paleoclimate can give us some information too. For example, now that we have seen the changes that we are causing and we can look back at the changes in the past, it is now virtually certain that no natural source of like orbital variations in the planet, like, you know, small changes in the Earth's orbit and so on, that are going to happen because we're not in control of things like the orbit of the planet, they're not going to be able to cause an ice age for at least 1,000 more years. Okay, we just we're not going to anytime in the next 1,000 years move into an ice age. That's actually important. You may have heard of this controversy that at one time in the 70s there were some scientists who were concerned that the planet was in fact headed back into an ice age. But now we know that now that we have a better handle on like what changes in the Earth's orbit are happening and so on, we now know at least for the next 1,000 years we don't need to be worried about an ice age. In part, of course, because we're warming the planet so much, it's just not going to happen. All right, paleoclimate stuff rocks. This is a really cool subdiscipline within atmospheric sciences. Excuse me. Please let me know if you have any questions about this stuff, and good luck on quiz number 2.